start off. Oops, I didn't set my markers ahead of time. I'm going to start off today talking about biosensors. So again, where I'm coming at this from a point of view, of course, is as an FSCV person who's primarily done FSCV, but we're now talking about kind of competing techniques. And again, I'm not going to give you all the details of the latest and greatest, best, news of biosensors, but I'm going to tell you the basics and then hopefully talk a little bit about how it compares back to our direct electrochemistry. And so in biosensors, we really put nature to work, and we use enzymes typically, although I'll talk about how they get away from them sometimes. And they put an enzyme on the surface of the electrode. And that enzyme then, when it detects whatever your analyte is, typically will make some sort of electroactive product, and we'll be able to detect that using electrochemistry. Again, all I'm talking about today are electrochemical biosensors. There may be fluorescent biosensors or other things, but in this example, we're going to talk about electrochemical ones. Okay, so let's look at an example of a reaction that we might have. So what if we took glutamate plus water plus oxygen, and we give it, the enzyme here is glutamate oxidase. Sorry, you can do it for glucose too, but it's glutamate oxidase. And what we'll make is hydrogen peroxide plus alpha ketoglutarate plus ammonia. So the electroactive product here is this hydrogen peroxide, right? And so we can detect that electrochemically. And there's a fair amount of these. This is just, it happens to be an oxidase. Again, there's a fair amount of oxidases. There's dehydrogenases, and there's some other ones that make other products too. But I just thought I'd throw this up there. The Renton Lab, I think, has published exactly one biosensor paper, and this is what we did. So we've made this sensor before. We can make this in our lab if we want to. And so this is just an example, though, of how you would detect a neurotransmitter, right, as far as you go along. And so, again, if we want to detect this electrochemically, we'll write out the reaction for hydrogen peroxide. It goes to 2 H plus O2 plus 2 electrons. And so, yeah, so that's the electrochemical detection. And so, I need more space. All right, I think I'll erase that. So with the biosensors then, if you were to look at that reaction, I should probably plan up for it better so I didn't have to erase it, but we're going to do it in just a different form. So imagine you have glutamate here, and it's going to go, the main product, right, is the alpha ketoglutarate. Right, that's the main product, and we got some side things as well. Right, and so to do that, we need our enzyme, right, and as we do that, that enzyme's making hydrogen peroxide, right, which eventually we can make oxygen, and this is going to be my electrode surface, right, and I'm going to get electrons, well, I'm just going to put one electron there, electrons flowing that way. So again, we kind of have these kind of cycles and the enzymes in the middle, and we're going to do here some sort of direct detection, and if we do that, this is called a first generation biosensor, just in case you see that terminology. So this is just where, the simplest thing, I make something direct detection, I then do an electrochemical reaction. With a second generation biosensor, now we're going to throw in the use of some sort of mediator. So something else to help carry the electrons. And so we're still going to have our glutamate going to our alpha ketoglutarate. I can't spell. I want to put them both as glue, but they're not exactly the same glue. Right, and so we're still got the enzyme that's helping us do that. But now there's typically some sort of mediator that's going to help us with the hydrogen peroxide reaction. And again, we have an electrode here, and we're going to have electrons flowing to the electrode. And so typical, I mean, I looked up a couple papers like metals, right, osmium, or something else that you can do a fairly good reaction there. And so they use mediators, and they use mediators because sometimes it's easier to oxidize and reduce the mediator. And there's a horseradish peroxidase reaction that they often use a mediator with to detect hydrogen peroxide. Okay, so that's a second generation if you want to throw in a mediator. What they often call third generation is where they try to do direct electron transfer to the enzyme. So now, rather than trying to detect hydrogen peroxide or mediator, oxidizing hydrogen peroxide, we're going to try and see if we can't get a direct kind of thing. So we still got our glutamate going, our alpha-ketoglutarate, and we have an enzyme. But now we're hoping that enzyme has some sort of reduction and oxidation state of the enzyme itself. And so as we transfer electrons and do this reaction, we'll get electrons flowing directly. As you can imagine, if you could theoretically have the right enzyme and do this, it's simple, but it's also really hard to get an enzyme in the right capacity and kind of orientation so that it's close enough that it wants to transfer enzymes. And then, just in case you want to know what the next one is, haha, it's not fourth. They're often called next generation, and these are the no enzyme biosensors. So now, what if you say, I don't want an enzyme, that's big and bulky. I'll just take like the metal center or something out of the enzyme, the functional part, and do it. And so we're still going to have our same example reaction. We're going to glutamate to alpha-ketoglutarate. But now they typically have a metal or metal oxide instead of the glutamate. And this metal oxide can exist in reduced and oxidized forms. And again, at our electrode, we can get electrons to flow. So an example of a reaction here might be something like this: nickel hydroxide plus base, OH minus, goes to NiOH plus water plus an electron. And so this again, it can be oxidized or reduced to form those products and help us be able to detect things. So there's a lot of work in the inorganic field on like enzyme mimetics, right, with inorganic type metals, metal oxides, that kind of thing. And so some of that's in biosensors now too. And so these, so you'll find people like, oh, I mean, an enzymless biosensor, right, and it's usually based off of principles from the sensor. So how do we get an enzyme on the surface? The typical kind of answer to that to put the enzyme kind of and localize it on the surface, typically the answer is in a polymer layer. Again, this is where the literature would have 1,000 different approaches to do it. You might be able to directly tag it, do some sort of genetic tag or something where you can put an amino acid that you can tag to. But typically there's like layers of polymers. Oftentimes now the latest and greatest often use things like graphene and other nanomaterials The reason to do something like that is just, again, to have more conductive material that's kind of out from the electrode that you might be able to, you know, kind of be closer to an enzyme or the hydrogen peroxide and be able to tell it, to detect it. The geometry of these is pretty flexible. There's a fair amount of literature with biosensor arrays, right, and maybe not even the same biosensor on each part of the array. Like you can make a, you know, MEMS kind of silicon chip kind of printed device or something and put your biosensor on it. You can take a coated wire or carbon fiber, coat it with these things and make a biosensor and put it in vivo. So again, you're not limited to kind of one different geometry as far as that goes. So let's make a quick little chart. And look at some of the advantages and maybe disadvantages, pros and cons, so to speak, of enzyme sensors. So if you look at the selectivity, right, nature is beautiful. Nature has done a great job of making pretty selective enzymes. And so you have an enzyme, and so you have really high selectivity, right? And so you can tell apart different compounds with different enzymes really easily. The sensitivity, or limited detection, I would say also is usually pretty, well, LOD is pretty high. Again, it depends on the design and what you're doing, but these can be relatively sensitive. As I said, they've been used in lots of kind of biological clinical applications. Oftentimes you can get a fairly large range. I'll talk in the aptamers. It's not always linear because the enzyme kinetics, but you can get a large range that you can look at. And of course, compared to FSCV, it helps you detect analytes that are not electroactive, right? So I used glutamate as my example, and glutamate is an example of a compound that we can't detect with FSCV. It just does not oxidize within our window that we can use for carbon fibers. And so we can't just go directly detect glutamate, right? It doesn't work. And so, you know, of course, the big advantage of biosensors is if you can find the right enzyme and couple it to your, you know, electrode, you can make biosensors for a variety of different things. And I would say that maybe that's another thing, is that it's kind of a platform that in theory should be flexible for different enzymes, in theory. But, you know, if you knew how to make biosensors and you wanted to throw on, you know, glucose oxidase, lactate oxidase, right? You know, it's not starting from scratch. You may have to optimize conditions just a little bit, but it's kind of a general platform and way people make things. Disadvantages, I think one of the disadvantages is usually stability of the enzyme on a surface, right? So you're putting your enzyme in a very non-native location, it's probably a polymer, on a surface. And a lot of the biosensors you buy, if you buy them, they have a very limited range. Like if you buy them from a company, it's, you know, a couple weeks. If you make them, oftentimes they only keep good for a week, and you got to keep it in the right solution or cold, that kind of thing. But you know, they're a little finicky, you know, because of enzymes. And then adding to that, they have been used in vivo, but I think the harder part is to think about any sort of long-term in vivo. I had a friend that was working at a national lab trying to do kind of like implantable like biosensors. I think it was for glucose, and she wanted them to last a week. And boy, were they having difficulty, right? You know, a day maybe, a week, no. Right, you know, they just would break down in the body in a way that they didn't really work. And so, as I said, they've got a lot of advantages, and they're pretty, I don't know, mature technology now. A lot of people have made them for a while. I think the future here what you always kind of hear about are the wearables, right? Where you can make a biosensor, excuse me, and put it on like a patch, and then, you know, like detect something on your skin or in your sweat. And so those are kind of, you know, people are always trying to put these on kind of flexible biosensors. And as I said, it's a really nice general platform where that's where kind of the commercialized is going. And just an example, and this is not a complete list, but of the things that I know there are biosensors for. Again, glucose was the #1 thing that people developed. Good old diabetes, right? You know, still same technology, kind of in a glucose meter that you use today. As I said, glutamate, for us brain people, comes right behind. Again, if you're worried about energy balance, glucose and lactate tell you a lot. And so Martin Mutel and a lot of other groups have done a lot of biosensors for those technologies. Nick Dale, our lab is really interested in adenosine, and Nick Dale's group developed both adenosine and ATP biosensors, and so you can look at those as well. And then there's been biosensors developed for dopamine, some of the other catecholamines, serotonin, etc., etc. And so most of the common small molecule neurotransmitters that we look at all the time, probably somebody's developed a biosensor for it. And so if you think about FSCV, right, we get direct detection, so we're often a little bit faster, as I said, and quite frankly easier. We don't have to go through all the rigmarole of making a biosensor. But FSCV, I think, loses on selectivity, obviously. Like, we don't get the beautiful selectivity that a biosensor has. And again, I think it just really depends on what you're looking for and your application. As I said, I think for dopamine, direct detection still rules the roost, right? You know, most people don't want to go through the effort of making a biosensor when you can do it so easily directly. But for some of the other ones that are more difficult to do directly, or you're really worried about selectivity, like if you really want a selectivity between adenosine and ATP, you're going to have much better selectivity on the biosensor than you are going to have with FSCV. And so I think that, as I said, it's always good to use and know about competing technologies so that we are able to kind of compare them back to what we do on a regular basis.